So our next speaker is Graur from NYU in the American Museum of Natural History.
Okay, so I'll be describing a method to turn any massive spectroscopic galaxy survey into a transient survey for free. And let me just start by thanking the organizers for this meeting. I'm just entering this field. I'm mostly a supernova person, so this has been very educational for me. Which also means that in order to describe this method, I'll have to take you through type 1a supernovae for a bit, and then I promise we'll get back to TDEs. So as Yair mentioned on Sunday during the school, most transient surveys today follow three main stages. We have an imaging survey, which we use for discovery, usually using difference imaging. And with this, we don't find supernovae or TDEs or anything at all. Really, we find candidates. We then go on and classify these candidates, usually using spectroscopy, together with more imaging in order to get the light curves. And if the object turns out to be interesting, we go on to stage 3, where we follow up with even more imaging and spectroscopy. This is efficient, but it's also very expensive. And it's not always the best way to go about it. So this is an example from the Subaru Deep Field. This is a supernova candidate. However, this over here is a subtraction artifact. These are also subtraction artifacts. And Barak will talk a bit more about what you do with those. What I want to show you is how spectroscopic galaxy surveys can actually combine the first two stages, discovery and classification, into just one stage. And not only that, but you do it for free because you piggyback on existing galaxy surveys instead of building your own cameras and surveys. So in order to do this, you need some method to tease out the transient signals out of your galaxy spectra. So I have such a method. In gray is an SDSS spectrum of a galaxy. In yellow, you see a galaxy model that's been fit to this spectrum. It's fit using a linear combination of galaxy eigenspectra, so it's fast and efficient. And it doesn't do a very good job because lying inside this spectrum is also a very bright transient, which you can tease out once you add supernova templates to the galaxy eigenspectra fit. And then you get the blue fit, which can account for both of these. And then in the bottom, the gray spectrum is now the original SDSS spectrum minus the best fitting galaxy model. And in red is a best fitting type 1a supernova. So you can do this. You can find supernovae, other types of transients in galaxy spectra. In fact, you can find quite a few of those because SDSS collected nearly 1 million galaxy spectra, actually around 700,000. You can find about 100 type 1As, a few dozen type 2 supernovae, and actually much more than 1,000 active galactic nuclei if you optimize for AGNs. And you don't need the supernova to be brighter than the galaxy itself. I can go down to objects that are about 10% as bright as the galaxy. Now, finding these objects is nice, but 100 supernovae doesn't make for an exciting survey. PTF, PanSTARRS, all of these surveys today find a lot more. In the era of LSST, this will be a drop in the bucket. However, these galaxy surveys also get you information about the galaxies themselves for free. And if you have a good pipeline reducing the information from these spectra, you can get good information about the galaxies. You can get stellar masses, star formation rates, star formation histories, metallicities, whatever else you can think of that you can extract from a spectrum. So I'm just going to show how you can use this type of survey to answer an interesting question. So back in 2011, Lee et al. Published a series of papers showing results from the Lick Observatory supernova search. This is a search that at the time was going on for more than a decade. They found hundreds of supernovae. These were relatively nearby, out to about 100 megaparsecs. Very efficient, very nice. A lot of very interesting supernovae came out of that survey. And they used the galaxy's colors to measure galaxy masses, and they computed rates per unit mass, which is what you see here, for different types of galaxies. And for all of those, they found a puzzling anti-correlation. You would expect that if you normalize your rates by stellar mass and then plot them as a function of stellar mass, they would be constant. Instead, they decline with increasing galaxy stellar mass for all supernova types in all types of galaxies. And at the time, they didn't quite know how to explain this. They thought it was somehow connected to specific star formation rates, at least for core collapse supernovae, but they really didn't know what to do with the type 1a supernova. So this connects to a deeper and more longer-lasting question about type 1a supernovae, and really about most supernovae, which is that we don't know their progenitors. We don't know what types of stellar systems end up exploding as different types of supernovae. For type 1as, this is a long-standing problem because, as everyone knows, we use these for cosmology, and not knowing exactly what type of star explodes is kind of a systematic uncertainty. There are different ideas out there for what the stellar system may be, and even though we're in Israel, Noam Soker isn't here, so I can mention just the two leading ones. We think that what explodes is a white dwarf, but you need to somehow destabilize it. So you put it in a binary system, and you either accrete matter from a main sequence or a giant star until you reach a high enough temperature and pressure in the core so that you ignite the carbon, or you put the white dwarf next to another one, and the two spiral in and either merge or collide due to loss of energy and angular momentum to gravitational waves. So if you take a model, a very simple model that combines galaxy downsizing, which means that more massive galaxies tend to be older than younger galaxies, and combine that with the delay time distribution you expect for type 1a supernovae based on measurements, you can explain this rate-mass relation away. So these are supernova rates measured with those 100 type 1a supernovae I found in the SDSS. They confirm the rate-mass relation found by loss, and the gray curve shown here is the best fitting rate simulation based on that model I showed you. So galaxy downsizing and the delay time distribution for 1As. And this is all very nice, right? But this isn't very different from loss. Again, this is just rates as a function of stellar mass. But as I told you, with SDSS, you can also get star formation rates and specific star formation rates. And you can rebin your rates and just show them as a function of these galaxy properties. And then you get these measurements over here. And once again, the rate simulation is shown as a gray curve. However, this time, it hasn't been fit to the measurements. It's only been rebinned, just like the measurements themselves, from the fit to the rates as a function of galaxy stellar mass. and it's still very consistent with the rates, which goes to show that this is not just a consistent explanation, it's also self-consistent. And it has a very interesting behavior, which you can understand once you plot stellar mass as a function of these galaxy properties. And then you can just see how this model works. So if you remember that the delay time distribution is a declining power law, this means that most type 1a supernovae are actually produced very shortly after star formation. About half of all type 1as are produced less than 500 megayears after star formation. And as you go to longer and longer delay times from star formation, the number of type 1as you produce goes down. So now, if we look at these rates, we see that when we start with galaxies of 10 to the 10 solar masses and we go up in star formation rates, we're actually sampling more and more massive galaxies. Okay, which means that, yes?
A little concerned by the sort of extrapolated excess in supernova rate on the top left diagram.
Over here?
Yeah.
It's actually consistent with the one type 1a supernova I have in that range, which isn't saying much. So if you go from less massive to more massive galaxies, that means your galaxies are also getting older, okay, which means there's, and I should say this is SDSS, so you can think of all these galaxies as being sampled at the same redshift. Okay, so when it's older, that means there's more time between when the galaxies were formed and the time you observe them. So the delay time distribution has a longer time to operate, and you're seeing a reduction in the rates. And then when you're going further up in star formation rates, you're going from passive, massive galaxies down to less massive star-forming galaxies. You're going down in mass, which means you're going down in age, and the rates go up, and so on. Yes?
Where would the delay time distribution turn over? So you showed the delay time distribution before, right?
Mm-hmm.
So this would extend as a power law to where
We assume that it turns on at 40 megayears. So yeah, the time it takes for an 8 solar mass star to evolve to a white dwarf. And before that, you have nothing.
Yeah, I'm just thinking that there are some models where it turns over hundreds of megayears.
Those would probably give you just as good a fit. Okay, so this was just to show the kinds of experiments you can do with these types of transient samples you find in galaxy surveys. Okay, it's not that you're not only finding transients, you're finding them in the host galaxies, and you're already collecting information on the host galaxies themselves. You don't have to go back and sample them after the fact. So we can do archival surveys on surveys where the data already exists and is public. The leading ones are, of course, SDSS. The first and second iterations contain about 700,000 galaxy spectra. They're at low redshift, up to 0.2, a median of 0.1. And there are several pipelines that give you galaxy properties. And of course, you can write your own. SDSS-3 had the baryon oscillation spectroscopic survey, which had 1.5 million galaxies, so double the number in SDSS. The redshifts here are actually incorrect. This goes much higher. The median is at 0.6. And EBOS, which is ongoing, is much smaller. It's only about 250,000 galaxies, also at higher redshifts. What's more interesting is the upcoming galaxy surveys, which are going to be much larger and a bit more interesting. So the Subaru telescope has already installed the new Hyper Supreme camera, and they have an imaging survey for transients going on. They're still working on the prime focus spectrograph, but when that's done, they'll have at least 2 surveys, one looking for emission line galaxies at redshifts up to 2.4, and there'll be 4 million of these, and 500,000 galaxies at redshifts between 1 and 2 for galaxy evolution. They expect that these 4 million galaxies at least will have not just the lines but also the continuum. As long as you actually sample the continuum, you can find transients. But what's really exciting is the Dark Energy Spectroscopic Instrument, or DESI. DESI will go online in 2018. It'll be installed on the 4-meter Mayall telescope, and it will have 3 types of samples. The most interesting one for us in this room will be the bright galaxy sample, which will have 10 million galaxies between redshifts 0 and 0.4 at a median of 0.2. These will be bright galaxies, brighter than 19.5 in the R band. You can think of this as a much larger SDSS at a slightly higher redshift. There will also be luminous red galaxies and emission line galaxies at higher redshifts. Now, based on our very broad understanding of what TDE rates might be, okay, assuming 10 to the 4 to 10 to the 5, 1 every 10 to the 4 to 10 to the 5 years per galaxy, if you just take the number of galaxies in SDSS, BOSS, and DESI, and you select only those galaxies with stellar masses so that the supermassive black hole will be less massive than 10 to the 8, you naively expect to find a few in SDSS and BOSS, and dozens up to maybe 100 in DESI. Now, in SDSS, we already know that we can do this because Stephanie has done this based on the high ionization iron lines. But this spectrum of SDSS 0748, as Yair also mentioned, was interesting because you not only have these high ionization emission lines, but they're also sitting on these broad H alpha and helium-2 components, which we see in some of the other TDE spectra. And so a few months ago, I came up to Yair very naively, and I said, oh, okay, so we know what TDEs look like now. We have TDE spectra of them. I can just fit this into my code instead of the supernova templates, and we'll just run through SDSS and BOSS, and no problem, we'll have probably about 10 new TDEs in a few weeks. So, no. But during the supernova survey, I did have one interesting candidate, which my code thought was a type 2N supernova, which immediately means it's suspicious, because I only have 2 type 2N templates. They're problematic, and calling something a 2N doesn't mean much. So we started looking at this in a bit more detail. So first of all, in the top panel, in black is the SDSS spectrum. In green is a galaxy-only model. And Yair, this would mean that this is a star-forming galaxy, because you do have these narrow lines that are fit. This is what the transient might look like if you assume that there is indeed a transient signal on top of the supernova here. You have a broad H alpha component, you have H beta, and you also have a broad helium-2 component. And the red line is the type 2N template. It's a bit hard to see, but it predicts another feature that you don't quite see here. It's not exactly what you would expect from a type 2N. So Yair was very nice to immediately plot this together with the other TDEs, and immediately you start running into problems. The lines are broad, but are actually narrower than most of the other TDEs, with maybe the exception of TDE2 from Schur's work. So I said, okay, you know what? Let's take some follow-up spectra. Let's just see if it's there or not, because the first thing I thought it was actually an AGN. So the original SDSS spectrum is from 2006. The transient part is shown in black. In 2014, we got an MMT spectrum, which showed that the age alpha was still there, maybe narrower slightly, and the helium-2 component was now actually broader. So that was weird. And then a year after that, Mariam was observing some of her targets at Keck and ran out of targets somewhere near the end of the night, so observed this for me again. And you can see that the age alpha is still there, but the helium-2 component, if it's there, has declined quite a bit. So if this is a real object, it's maybe been alive for more than a decade. Slightly weird. So maybe this is not a TDE. Maybe this is something else. Few things we need to look at. So first of all, this was found in the center of an SDSS galaxy, which is all well and good, except that the fiber aperture has a diameter of 3 arcseconds, which means 1 kiloparsec at the distance to this galaxy. So it doesn't have to be in the nucleus. There's the broad lines we mentioned, but they're not as broad as some of the other TDEs. The hydrogen is still present a decade after first detection. The helium-2 component seems to have broadened and gone fainter. There's no AGN here if you use the BPT diagnostic. There's some star formation in the galaxy, so not exactly what we expect from the E+A-ish. They don't have to be. There is a radio detection from first, but we've heard that maybe you have an acquiescent AGN before these flares happen. But there's no photometric variability for more than a year in the middle between those different spectra that I showed you, according to PTF. But maybe we're seeing more than one flare. And on top of all of that, this galaxy is also, these lines are completely consistent with this being a Wolf-Rayet galaxy. And there's a very slight excess in the X-rays. So in other words, while I've been working not too hard this past year to try and kill this candidate, I don't think we can. I don't think we can say either way whether this could be a TDE candidate or not, which leads me to my final conclusions. First of all, you can turn any massive spectroscopic galaxy survey into a transient survey and do that for free. There's an expectation that we should find a very nice number of such objects, especially in DESI, but also in SDSS. And there are many more such surveys in the near and far future that we can exploit. However, real-time multi-wavelength follow-up will be crucial, which means that this will only really come to fruition in DESI, where this kind of survey will be done in real time. So let me just give a shout out to the American Museum of Natural History. We have an ongoing exhibition about extremophiles. This is a tardigrade. These things can survive the vacuum of space. It would be interesting to simulate what would happen to this little thing if you threw it too close to the tidal radius. And I would just say that I think we're going to hear a few more stories of amazing transients in nuclear centers. So thank you.
Okay.
They said star formation. They have some radio machines. Where does it fall in the radio far-infrared correlation?
I don't know. Good question.
I mean, the radio could be coming just from star formation itself.
Could be.
If it's used in the emitting spectra, has it changed in
So these aren't flux calibrated. So the MMT is, so it looks like even if it hadn't declined appreciably, it has gone, yeah, it's gone cooler, whatever this is. But the Keck spectrum definitely isn't flux calibrated, so don't trust that.
Next question. Can't you localize it better now? It's still visible at the present day. It's showing an excess in the spectra.
So we can, and about a month or two from now, we'll start observing this with LCOGT to see if it's still visible, still variable, and if so, we'll think about localizing it better.
But you put the slit in the center of the galaxy, or it's again integrated?
No, the slit from both of these is on the center of the galaxy. But again, if it's a 2 arc-second slit.
Yeah. Okay. Thank you all.
Okay, thank you.